Hello, welcome to The Naked Scientists with me, Chris Smith, and with Dominic Ford. Hello, Dominic.
Hello, and this week, why malaria is giving mosquitoes the munchies, the chemicals which are putting seabirds at risk, and how being selfish may have triggered the farming revolution.
Plus, we put meteorologists under pressure in our quest to find out how the weather is forecasted.
If you'd like to get in touch with us here at The Naked Scientists, email chris@thenakedscientist.com, tweet @nakedscientists, or you can find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
And joining Dominic and me to take a look at this week's top science news stories is Victoria Gill, who's a BBC science reporter. Hello, Victoria.
Hello.
But before we come to your story, water. And scientists this week have announced they have found the oldest samples of water on Earth. This is a water sample which is 2.64 billion years old. Now, where have they found this? Well, it's down a copper and zinc mine, 3 kilometres down underneath the town of Timmins, Canada. And this water was collected very carefully so that there was no chance of it being contaminated by air from the outside world. And this group who've done this work, which is led by Chris Ballantyne, who's a geochemist at the University of Manchester, have analysed the water. And in particular, they have looked at chemical isotopes, in other words, different forms of the same chemical, which can tell us what something's history is in terms of its contact with the outside world. And the picture this paints for us is of water which has been trapped underground for at least 1.5 billion years, if not 2.5 billion years.
How do they date it that far back? What exactly are they looking for as a signature of that age?
Well, you can look at different forms. In this case, they've looked at noble gases. So they're looking at xenon principally and some other isotopes as well. And we know how they have changed based on what is in the atmosphere now, what is in trapped bubbles of the atmosphere in other rocks around the world from time going back, and what is in this present sample. And if you compare all of these together, they've taken 3 different lines of attack on this. You can resolve all of these independent lines of evidence back to about 2.64 billion years. Now, why this is also very interesting is that the water is absolutely crammed with hydrogen and methane. And these 2 gases, we know, are very fertile bacterial food. And why this is important is that in 2006, there was a lady called Lisa Pratt who got water from a mine in South Africa, also about 3 kilometres underground. And in this water, which they could prove using similar techniques, had not been in contact with the outside world for more than 40 million years, there were thriving communities of microbes. And they were living on the hydrogen from what we call radiolysis of water. The rocks are naturally radioactive, and the radioactivity of the rocks breaks open water molecules and makes hydrogen that the bacteria were feeding on. So this suggests that, they haven't announced this yet, but they're going to be analysing this water to see if there's evidence of life in there. Because if there is, we've got this big body of water underground, and the sort of geology that trapped it, a series of volcanoes over millions of years in Canada, is also going on other planets in our solar system. Mars is a really good example. We know that was very geologically active. There could well be very large bodies of water under the ground of Mars, and they could also have the same sort of chemical makeup, and therefore if there's life in this water, it really raises the stakes for finding water elsewhere, such as on places like Mars too.
Now, Victoria, I gather you've been looking at a paper about pollution causing problems for seabirds. What's that about?
Well, it's sort of news that's been discussed for the last few weeks, actually. I don't know if you recall, but it was reasonably big news in the UK that these poor, unfortunate seabirds started washing up on our south coast, covered in this mysterious gluey substance. And the RSPB, who were looking into this, really didn't know what this stuff was. And it turns out that over a few weeks of doing chemical tests on these birds and trying to get them cleaned off and help them, that this stuff is this incredibly ubiquitous chemical called polyisobutene or polyisobutylene. It's a synthetic rubber, and it's used in chewing gum, it's used in cling film, but it's also used to clean out ships' tanks because it's very sticky and cloying and can get into the corners and reach other parts that more toxic chemicals even can't reach. It's completely non-toxic as well. So a lot of these ships, it seems, might have been discharging quantities of this PIB, this polyisobutene, into the water, and then it's kind of conglomerating because it's very, very hydrophobic. It repels all the water away and conglomerates in big blobs, and it's as the seabirds sort of dive around where this stuff is floating in layers, they're getting it all over their feathers. So actually the RSPB are saying they want it banned so that it can protect marine life in the future.
Isn't there a danger, Victoria, that if we ban it, then they've still got to clean their tanks on ships and lubricate their engines and things, so they'll just find something else to use which may be equally damaging?
Or more damaging, or damaging in a very different way, because the thing about this stuff is that PIB is completely non-toxic. Like I said, it's used in chewing gum, so, you've probably chewed it at some point in your life. And so, yeah, it's a concern that there might not be something that's as easy to use and as effective to replace it. But what they're saying is that at the moment, there might be cases where it's being legally discharged very close to the coast because it's being discharged in this kind of limited quantities at a reasonable distance. And because it conglomerates in this way, it's sort of just floating in these blobs. And then the seabirds are being really particularly affected because they're diving through it. So they think it's injured or killed about 4,000 seabirds. And there's probably countless that are out offshore that haven't washed up on beaches that have died because of this. So what they want is regulations to say that ships aren't allowed to discharge it in the sea at all. And then they can put some other kind of practice in place whereby people can be helped to kind of legally clean out their tanks and legally discharge this stuff on shore and dispose of it safely.
That's not going to go down very well with the ship owners, though, is it? Because it's enormous cost, and it means that then they don't have the convenience of being able to just chuck it away at sea.
Well, yeah, there's practicality issues in there. Although there was a big call that went out from the RSPB and the RSPCA and the Marine Conservation Service, and it was also supported by the UK Chamber for Shipping. So the industry body is actually saying, yes, we're going to get behind this, and we want to be behind good practice. So they obviously want to get involved with having the regulations in place so that the investment goes into shipping, so that the people that are actually investing in doing things properly get the money behind them, and they're able to get different materials to be able to clean out their tanks and lubricate their engines in a safe and sort of marine environment friendly way.
Thanks, Vic. Well, it all comes down to greed, doesn't it? Which may actually, Dominic, interestingly, underlie where we actually got farming from in the first place.
That's right. Now, 12,000 years ago, there was a quite interesting change in the way that our ancestors were behaving. Up until that point, we'd been picking the food that we eat out of the natural world around us. We'd gone chasing after mammoths with spears. And rather than preparing crops in fields and planning for the future, we'd been living a hand-to-mouth existence from day to day. And at that point, we started farming. We started burying seeds in the ground so that we would have food the next year. And the question is, why did that change happen when it happened in about 10,000 BC? And people have put lots of ideas forward for what might have changed at that time. Some people say it might have just been an easier living to grow crops so that you don't have to always worry about where your next mammoth is going to come from. But in fact, if you look at the archaeological remains of people who were the first farmers, they were often less well nourished than the farmer-gatherers around them. They don't seem to have had an easy time with lots of food. Other people have said perhaps it was about land economy, because if you're farming the land, you're making much more efficient use of every acre of land you've got. But if you look at the populations 10,000 years ago, in fact, the world's population was declining. There wasn't that much pressure on land use. Now, still other people have said perhaps it was technology, perhaps new tools became available that made farming possible. But once again, that doesn't really stand up to the evidence, because you don't really need very sophisticated tools to farm land. You need a plough and you need seeds. And actually a spear to kill a mammoth is arguably a much more advanced tool. So writing in the journal PNAS this week, Samuel Bowles has argued that actually it may have been a change in our psychology that led to farming. People became much more possessive. They wanted their land with their food, and they didn't want to share it with the community.
Why would this suddenly come along now at this point in time, this possessiveness that wasn't there before then?
That's quite a hard question to answer, and one of the problems is that people's behaviour doesn't always leave a very clear signature in the archaeological record. Samuel Bowles argues that once some people had started farming, it would probably take over the community quite quickly, because it's much easier to raise children if you're settled on a farm than it is if you're roaming the land looking for mammoth. So if these people were breeding much more successfully on the farms, then just by sheer numbers, within a few generations, most of the people would have been farmers.
And then we get sort of hooked on that way of life, because once you've got farmers you're depending on, you lose the skills to go and fend for yourself. Is that the argument?
That's right. So he's arguing that this is an accident that was waiting to happen. At some point, some people started farming, and once that had happened, they took over.
Well, brown-earthed brown butterflies. Victoria, it looks like butterflies that are brown fly further. What's this all about?
And this is a really fun study in the Journal of Behavioural Ecology. It's the Northern Hemisphere, at least, it's migration season at the moment. And I was looking at this paper about the monarch butterfly by these researchers at the University of Guelph in Canada. And monarch butterflies are, as well as incredibly beautiful, they carry out these really spectacular migrations. They migrate in huge numbers all the way from Canada across the States to Mexico. But some get further than others. And this might have a link to their coloration. How far they travel might be linked to what colour they are. These researchers took samples of butterflies that they found in the Great Lakes halfway across on that migration, and then butterflies they found in the Gulf of Mexico. And they found that the ones in the Gulf of Mexico were significantly more pigmented. They had more of this melanin pigment, this reddish brown and dark pigment in their wings. So it seems that the more pigmented, the more colourful butterflies go further. But they go a little bit further than that in their hypothesis about this. What they suggest is that this pigment could be fueling them in some way. Because these butterflies are darker, their wings are absorbing more heat, and that might be giving them the thermal boost, that thermal energy, to go on a much longer journey than their counterparts.
Could also be an epiphenomenon, though, couldn't it? In the sense that you've got this brown pigmentation. It's not the brown pigmentation that makes the butterflies go further. It does something else to them, and it's the something else it does that makes them faster, fitter, able to fly for longer.
It could indeed. It's the classic cause and effect issue. I mean, he started looking at this off the back of he's a behavioural ecologist, very interested in how these animals behave and getting to the fundamentals of the biology. But he started looking at this because a couple of years ago there was a study that found that the temperature at which the caterpillars were raised actually affected what colour the butterflies were. So caterpillars that were raised in warmer temperatures had more of this melanin pigment, were browner and darker and brighter, was more dramatically coloured butterflies. So he's trying to pick apart how this affects their life cycle as a whole. So the next step will be to try and bring this energy expenditure into the lab and just see if there's an effect on how far the butterflies can travel, how much energy they actually have when they pick up this thermal energy in their wings.
Well, I'm going to finish with something else that flies, and that's mosquitoes. Mosquitoes are actually judged to be one of the most dangerous creatures on Earth because actually they account for more deaths than any other creature. There's about 200 or 300 million cases of malaria around the world every year, and up to 1 million people die of it. And malaria is, of course, exclusively spread by mosquitoes. And in the case of falciparum malaria, the most deadly form, that's Anopheline mosquitoes. But what does the malaria in the mosquito actually do to the behaviour of the mosquito? That was a question that was bugging, excuse the pun, James Logan and his team. They're a research group based at the London School of Hygiene and Tropical Medicine. And in PLOS One this week, they actually show that being infected with malaria gives mosquitoes the munchies and makes them much more likely to home in on the smell of a human. So they do a very elegant, very simple experiment. They put 2 nylon membranes in front of these mosquitoes. One of those nylon membranes, which resembles human skin, has been tainted so it expresses the same smell characteristics as human skin. The other hasn't. And they compare how many mosquitoes land on and try to bite through the membrane, simulating a mosquito biting a person. And you tot it up over a period of time. You then repeat the experiment with mosquitoes that are infected with malaria, and what you find is that the malaria-infected mosquitoes bite 4 times more frequently compared with the mosquitoes that are free from malaria. The researchers say, well, it could be that the malaria parasite is in some way manipulating the smell or olfactory system in the mosquitoes. They don't know exactly how yet, but it's tantalising to suggest that perhaps they increase the sensitivity of the mosquito smell system to those odours that signal out a human to a mosquito. And that draws the mosquito to the person at the very time when it's most infectious, so it's more likely to pass on the infection. You can see there's a strong evolutionary reason why that might happen.
So how do they see this being applied?
So the argument would be, if this is the malaria parasite manipulating the behaviour of the mosquito, what it may be possible to do is to find out how it's doing that, and this may lead us to a whole new avenue of ways to prevent or cut down the risk of malaria transmission, effectively by blinding malaria-infected mosquitoes to humans. If you can reverse this effect, then you will reduce the rate at which malaria is passed on, and this will make the disease much easier to control.
Thanks, Chris, and thanks also to Victoria Gill. You can find more information, including references to the papers we discussed, on our website at thenakedscientist.com/news. Now, it emerged this week that actress and director Angelina Jolie chose to have a double mastectomy because she carries a gene called BRCA1, which greatly increases her chances of developing breast cancer. Here's your quickfire science about the story from Naked Scientists Elena Tay and Pete Skidmore.
Angelina Jolie carries a mutation in the BRCA1 gene, which stands for breast cancer susceptibility gene 1.
BRCA1, along with another gene which predisposes to breast cancer, BRCA2, belongs to a class of genes known as tumour suppressors.
These tumour suppressor genes encode proteins which are involved in the control of cell division, as well as in the repair of damaged DNA.
When mutations occur in these genes, the resulting proteins may lose their protective function, so DNA damage can accumulate and cell division may become uncontrolled. This can lead to the development of cancer.
Mutations in BRCA1 and BRCA2 are passed down through generations, and when a parent carries a faulty version, each of their children has a 50-50 chance of inheriting it.
Not all people with the faulty BRCA1 or BRCA2 genes will go on to develop cancer, but women with it are around 5 times more likely to develop breast cancer than those without. They're also at a higher risk of other forms of the disease, including cancer of the ovaries.
Men with harmful mutations in these genes are also more likely to develop breast, prostate and pancreatic cancer.
People with a family history of breast cancer can be genetically tested to find out if they carry the BRCA1 or BRCA2 mutations. This involves a blood test which looks for the defective changes.
There are a number of options for those who carry the mutations. Angelina Jolie opted for the double mastectomy, where most of the tissue is removed from both breasts, reducing her risk of cancer here to 5%.
Alternative treatments include using tamoxifen, a drug which blocks estrogen receptors in cells. This female hormone encourages the growth of breast cancer cells, so blocking it reduces the chances of getting the disease.
Elena Tay and Pete Skidmore. And Angelina Jolie has been widely praised for openly discussing her experiences of her mastectomy. Has she inspired you to find out more about your cancer susceptibility, or would you be too worried about what the results might reveal? Please let us know by emailing chris@thenakedscientist.com, or you can tweet at Naked Scientist, or of course find us on Facebook.
This is The Naked Scientist with Chris Smith and with me, Dominic Ford. In archives all over the world, there are shelves filled with old documents. Deeds, legal codes, inventories, parish registers, the list goes on. For as long as there's been parchment, there have been archives. But as scholars know only too well, these vast stores of historical evidence have also been storing up trouble for the future. Thousands of these documents have become so fragile that their contents are unreadable. That is, until now, thanks to the combined efforts of researchers from Cardiff University and Queen Mary University of London. James Harrison has been to find out more from the research team.
So I'm not sure of the exact age of this scroll. It's actually a rolled up parchment, so it didn't start life as a scroll, but once it's rolled up, as far as we're concerned, it is a scroll as far as the machine's concerned and all the technology we need to unravel it. I'm Graham Davies, reader in 3D X-ray imaging, Institute of Dentistry at Queen Mary University of London. And I'm actually standing here at what we call the MuCat-3 scanner, because it's our third generation of scanner that we've developed here. And this whole system here, this is obviously a lead-lined enclosure, so once this door is closed, there's going to be no X-ray leakage anyway. It's completely safe to sit here.
Nowadays, X-ray technology, used to look beyond what we can normally see with the naked eye, is a familiar procedure in medical diagnosis. Modern X-ray machines are now capable of creating three-dimensional scans using X-ray computed tomography, better known as CT scanning. Just as CT scanning has helped improve medical diagnosis, scientists are now proving its capability in the field of cultural heritage, especially in helping to reveal the content of parchment documents, which for hundreds of years have remained too delicate to unroll. Professor Tim Wess is from Cardiff University.
Parchment is skin, It's dried skin that's been salted and limed and stretched and beaten and had hot water poured over it, trying to make a smooth writing surface. And so understanding how molecules behave over hundreds of years is something that interests me, and parchment's been a fantastic vehicle to be able to study that. So working in that vein, I then got more and more involved with samples where the documents had effectively turned from the collagen into gelatin and actually glued themselves together.
Tim gave me a number of parchment samples, and these weren't actually scrolls, but we just rolled up a small piece, put it in a container, put it in the X-ray system, and sure enough we could see the ink on it. Now, we didn't have any means of unravelling it then. What we did have was some rendering software created at the Australia National University, would actually allow us to sort of slice it, and actually we could at least see the writing that was on the inside of the scroll or on the outside of it. And it looked so good that when we sent it to Tim, he thought this was some kind of mock-up, and I had to say to him, no, this is actually reconstructed from X-ray views of it, and he was quite impressed then, as was most people who'd seen it. So, that's what really got the ball rolling.
Once the first pioneering 3D scans were completed, the School of Computer Science at Cardiff University used computer modelling to present a flattened view of the documents, allowing a researcher to read what was on them, an exciting prospect for all concerned.
The first time that I saw that done, there is definitely, and it's one of those moments in your scientific career that sends shivers down your spine for the right reasons, and you don't get that many of those in your career, and seeing a flattened out document that we could all stand. I remember us standing out and we could all read it, and then handing that to the paleographer who can then go and interpret that and say what the impact of that is in terms of history, is a wonderful opportunity to have, and it's great to be part of that chain.
The moment clearly proved to be a significant turning point for historians and archivists and their ability to access historical information, with literally thousands of historical documents locked away in archives the world over, now available to the research community.
The support that we got from archivists who said, if this can be done, then it would actually revolutionise the way in which archives and difficult to access documents at archives could be, history could be recovered from, in a way that we don't actually know what some documents, the information on some documents, we can have a guess at what they contain, but if we can actually reveal that, it once again resets the priorities of how we might store them.
With funding from the Engineering and Physical Sciences Research Council, this innovative use of X-rays and three-dimensional microtomography gives us an unparalleled glimpse into our hidden past. And it's not just about simply detecting iron particles contained in medieval inks. What makes the technique stand out from other methods is the unprecedented high contrast resolution it provides to clearly distinguish between ink and parchment, meaning text is much clearer and therefore readable. The discovery has also proved beneficial back in the departments that first developed the technology. In relation to the human eye, for example, high-contrast X-ray microtomography has the potential to help ophthalmologists investigate problems relating to glaucoma. While for Graham Davis and his colleagues at Queen Mary's Institute of Dentistry, this enhanced scanning technique is helping advance aspects of dental research.
As well as developing the new scanner, we've made a number of improvements to existing scanners using our sort of own the technology that we've developed here. And that's already where we're using that in the dental research to see things in teeth that we hadn't seen before. And in fact, we've just got a paper just been accepted now talking about high contrast X-ray microtomography in dental research.
Back in the domain of cultural heritage, there are aspects of the new technology that still need to be improved. While the archive community has been excited by the prospect of at last being able to read inaccessible documents, there are still several developments required to make the machine practical.
The detector that we're using at the moment, the CCD detector, isn't the most efficient one. It's not the fastest, but it gives us the most accurate results, and that's why we've stuck with that. When we've got that, when we've shown feasibility that we can do this, then we start to think, can we make it faster? Can we make it portable so that we can transport this thing to museums or archives? Those are the sort of things that I think will come in future projects. But At this level, it was rarely we're asking the question, can this be done or can't it? We're on that narrow line between possibility and impossibility, and I hope we're on the right side of that line.
Graham Davies, reader in 3D X-ray imaging at the Institute of Dentistry based at Queen Mary University of London, ending that report by James Harrison. And his work was funded by the Engineering and Physical Sciences Research Council, and there is also an audio slideshow about that story. It's on the EPSRC's YouTube channel. You go to youtube.com/EPSRC video.
You're listening to The Naked Scientists with Dominic Ford and with Chris Smith.
Here in the Northern Hemisphere, summer is supposedly on its way, but we haven't seen very much evidence of that yet in Cambridge. Looking on the sunny side, though, we decided to find out how we forecast the weather so we'll know if it's going to be arriving any time soon. Dominic spoke to Brian Golding at the UK's forecasting centre, the Met Office.
Fundamentally, the weather of the whole world is driven by heat coming from the sun. And if that heat warmed up the Earth uniformly, then we wouldn't have any weather. But because some places absorb more heat than others, forests that are absorbing heat, oceans that are reflecting it, those variations in the heating then communicate themselves to the atmosphere. They result in differences in density, and different densities then drive the wind and the whole circulation of the atmosphere.
So I guess in trying to work out what the weather's going to do, are you basically simulating those processes to work out what's going to happen next?
Yes, that's exactly what we do. The mathematical equations that describe those processes are quite well known. Interestingly, though, if you solve those equations, they diverge into uncertain solutions. I like to say the atmosphere has a very bad memory, like me. So we always have to refresh the information about what the current state of the atmosphere is before we can start the forecast. And that's why we have lots of observations from all around the world and satellites looking down on the Earth, sensing what the state of the atmosphere is so that we can get the best starting point for a forecast.
And I guess it's interesting that, people have been interested in the weather for hundreds, if not thousands of years, and physicists understand how gas behaves quite well. So why is it so very difficult to solve these equations and work out what the weather's going to do tomorrow?
Yeah, it's a very interesting problem. It comes down to the fact that the atmosphere will respond to these variations in heating on a whole spectrum of scales. So at a very small scale, you'll get little eddies, which may turn into big eddies, turn into thunderstorms, perhaps with tornadoes. And then at the other end of the spectrum, you've got these large depressions that track across the globe. And in between, you've got a whole variety of scales of fronts and clouds. And when those interact with each other, then it becomes very difficult to make a precise prediction.
I know in the last year or so, the Met Office has moved over to using probabilities. So you talk about a 50% chance of rain rather than trying to say it will or won't rain. What do those probabilities mean exactly?
If we talk about the probability of rain, then what we're saying is that at the location that the forecast is for and the period that it's for, then there is a certain chance of having rain. The source of that uncertainty might come from a number of areas. It might be that it's going to rain for part of the time, but we don't know whether the time that it's going to be raining is during the time that the forecast is for or not. Or it might be that it's going to rain somewhere in the country, but we don't know what the chances are that it's going to rain in that particular location. Or it may be that the way in which the weather develops might result in rain, or it might not result in rain at all. And there are all these different sources of uncertainty.
Now, these physical processes that you're modelling to know what the weather's going to do, are they the same all around the globe, or are there specific physical phenomena that you have to worry about in specific geographic regions?
Yeah, fundamentally they're the same everywhere, but they do come in different mixtures in different parts of the world. So the equations are the same, but in developing the models, we have to optimize the performance by comparing it with what actually happens in well-studied situations. And that optimization has to be done for different parts of the world.
So how do you go about doing that?
The main way is large international field experiments where scientists choose a location and they set up observing facilities, often involving aircraft flights, to sample the atmosphere in great detail. They will involve the satellite observations that are available, surface observing equipment, and at the same time then they will run our forecast models for those same locations and carry out very detailed comparisons of what the forecast model produces and what's observed. By doing that, they can learn what the shortcomings are of the models, improve some of the details that go in the equations, parameters that relate to vegetation, for instance, or to the interaction with topography. And they might change those and look at how that alters the forecast and whether it makes it closer to the detailed analysis.
So does the same apply locally here?
Indeed. We had a detailed field experiment in the Welsh Borders a few years ago, looking at the way in which the atmosphere behaves on a clear night in winter. As the atmosphere cools down at night, then the wind tends to develop down the slopes of the valleys, bringing cold air down into the bottom of the valley. We did detailed observations of how that happened, and we compared it with the way in which the model developed. And one of the things that it told us, for instance, is that you really need to have a very fine resolution model in order to get that right, even finer than our finest models. So we have a 1.5 kilometre model at the moment. We would really like to go down to perhaps 200 or 300 metres when we can afford it, because we know it would produce a better forecast in those circumstances.
And what will that take?
It would require a computer with a factor of at least 100 greater power than we've currently got.
Thanks to Brian Golding from the Met Office. Brian might have modelling computers at his disposal, but do you try and monitor the weather from home? If so, we would like to hear how you do it. Do email chris@thenakedscientist.com. You can also tweet at Naked Scientists, or you can look us up on our Facebook page.
Now, Brian described how atmospheric pressure changes around the globe cause the weather we see on the ground, but some of these processes are still being researched. Ben Valsler spoke to Alison Ming, a PhD student at Cambridge University, about her work researching how air moves between atmospheric layers.
I'm working on the problem of tropical upwelling and what drives it. We know that air in the troposphere, so the lowest layer of the atmosphere we live in, air over the tropics rises up by convection because it's really warm there. And it carries on going, but at a certain point it hits the tropopause, and the tropopause is sort of that notional boundary between the troposphere, the layer below, and the stratosphere, the next layer above. So when it hits the tropopause, it carries on going into the stratosphere. What causes that air to carry on going into the stratosphere is still a question that is being debated, and that's what I'm working on.
So what is the structure of the atmosphere above us?
The layer we live in is called the troposphere, and the temperature really decreases upwards in the troposphere. Then the temperature sort of stabilizes and increases in the stratosphere. So there's an inversion of temperature. And people use that to therefore define a tropopause, which is that sort of notional boundary that sits between the troposphere and the stratosphere. And the tropopause is lower in the mid-latitudes, so above us it'll be about 10 kilometres high. In the tropics, it's much higher, it'll be about 15 kilometres.
So we've mentioned the troposphere and the stratosphere, but what's the difference and where's the boundary?
There are many ways in which you could separate the two layers of the atmosphere. So they're not obviously separated. There isn't a fixed boundary between the two. But you could use the different properties of them to define that tropopause. So one way of defining it would be using the temperature. There are other dynamical quantities that you could pick a value of and say, we'll take this value to be roughly where the tropopause sits.
Why do we think there needs to be a different mechanism? Why can't it just be more convection?
Some people think it's just more convection, but other people think that waves from just outside the tropics travel up to that region, break, and then pumps up the air. So that's a different pumping mechanism to air just rising because it's hot. And there's various other mechanisms that people think might be driving that upwelling, and I'm trying to figure out which one it is.
So why is it important to us? Why do we need to know what the process is that actually pushes this air up into the stratosphere?
Understanding the dynamics of the climate means that we then understand better how our models work. Also, it means that our weather models will also get better and understand what's going on in there.
So in terms of understanding our weather and understanding our climate, why is it important that we know what's going on up in the stratosphere?
In the past, people don't really think that the stratosphere mattered to what happens to us in the troposphere, and weather modelling didn't include stratospheric levels. But then we found that there was a hole in the ozone layer and discovered that if the ozone layer wasn't there, then we'd all be bombarded with UV radiation. But then also, there is a very slow circulation in the stratosphere, so air that goes up over the tropics then travels polewards very, very slowly. It takes up to 5 years to reach the poles, and then it falls back down. And that circulation has an indirect effect on the troposphere, and both the stratosphere and the troposphere are coupled together. And people found that by including the stratosphere into weather models, which is something that's only been done very recently, we could improve our predictions of weather.
So even though we in the UK are a very long way from the tropics where this upwelling is actually happening, there is an important dynamic process going on thousands of metres above us from thousands of miles away that can then impact not just the weather that we have, but the long-term weather trends, the climate.
Yes. Most of the stuff that gets into the stratosphere gets there through that tropical pipe. So things like CFCs, aerosol, pollutants, everything gets up to there via that tropical pipe. Those CFCs and other aerosols will eventually affect the radiative balance in the stratosphere and then eventually affect the climate in the troposphere. So one example I'd like to take is in 1991 there was a volcanic eruption, the Pinatubo eruption, and that volcano managed to inject quite a lot of dust and aerosols into the stratosphere. The few years following Pinatubo, the whole world was slightly cooler, mostly because there were lots of aerosols in the stratosphere. It's not an effect that was felt right after the eruption, but it was an effect that was also felt for many years after.
So it's obviously a very important thing for us to understand this global transport and the transport between different layers of the atmosphere. How are you actually going about it? What are you doing to study it?
What I do is I take a very simplistic model with 2 layers of the atmosphere, and what that model does is it models the very basic circulation around the planet. And then I look for specific features in my model results to see whether I can understand what drives the upwelling in that model. And then I look at an observational data set and see whether I can find those similar features. And if they do exist, then it's very likely that the dynamics that's happening in my model is similar to the dynamics happening in the real world.
Once we know that, what sorts of new questions will we be able to ask or hopefully answer?
One of the other questions I'm working on is just above the tropical tropopause, there is an annual cycle in temperatures. And if you think of it, the sun goes over the tropics twice a year. So there really should be a semi-annual cycle in temperatures. But as it happens, there's a very, very strong annual cycle. And that's the one other question that's also of interest to me and I'm working on. So hopefully, by better understanding tropical upwelling, then I'll be able to have a good stab at what is also causing that annual cycle.
Thanks to Alison Ming, who's currently completing her PhD at Cambridge University.
Despite the level of probability still involved in weather forecasting, sometimes there are weather events like severe flooding that we need to prepare for. To find out how we make sure that we see these events coming, Chris spoke to Nick Graham from the Met Office and started out by asking just what can be called extreme weather.
Well, the Met Office define extreme weather as heavy rain, severe gales, heavy snow, ice and also fog. All of those things can cause an impact on the UK.
How do you go about trying to predict them?
We have forecast models that we run here from the Met Office. We also see information from other forecasting centres. And the team of chief forecasters bring all that information together. And if we see something that's developing a few days in advance, then initially we'll take some action of beginning to inform people that there's a risk that there could be some extreme weather on the way. And then as we get nearer the time, say sort of 1 or 2 days in advance, we tend to get stronger signals. That means then we can sort of up the tempo, if you like, and we can begin to warn, we can begin to put things out through the media, and it sort of builds up from there. And we have a National Severe Weather Warning Service, which basically comes up with a colour, and that is the way of depicting the severity of the weather we're expecting.
How do you know, though, when you're looking at the information presented to you by a whole raft of measurements, obviously. How do you pick out from that the danger signals?
Take wind, for instance. To get very strong winds across the UK, you've got to have quite a major low-pressure system coming across the Atlantic. These systems almost start from nothing, but you begin to see the clouds sort of thickening up in the western side of the Atlantic. And when you get a major low pressure developing and pushing across the UK, you can almost estimate the amount of wind you're going to get as it hits the UK, and then that's when you begin to sort of nail down your information that goes into the warning service.
So where are you getting your information from? Obviously you're saying cloud cover, so you must be looking at satellite images, but what else?
Well, yeah, as I say, satellite images is quite a key aspect these days. We're also getting radar, so when we're forecasting heavy rain, our radar network across the UK is a very good indicator. Is that, just sorry to interrupt, but is that because basically radio waves get soaked up by water, and so you're looking at how much does or doesn't get bounced back? Well, it's a bouncing back off the raindrops, if you like. So when you send a sort of pulse of radar up into the atmosphere, then it bounces back off the raindrops. So the sort of bigger the bounce, the greater the amount of rain that's there. So that's one way of seeing it. And then, as I mentioned before, the forecast models from the computer these days, are pretty accurate. I mean, over the years, we've seen big improvements in forecasts. And in fact, our 4-day forecast these days is as good as a 1-day forecast was 30 years ago. And we see all this information, and it's then sort of bringing all that together, distilling it and say, OK, what does that mean for the public? And that's when we distill it into a warning on the Met Office website.
But obviously you've got quite a lot of power there, because in your hands is warning people to deploy various resources and potentially spend a lot of money defending against something that hasn't even happened yet. So you're in quite a stressful position, aren't you?
Well, what we do is share the information, the sort of weather information, with other teams. So if we take rain, for instance, ourselves and the Environment Agency work together. In fact, in the Met Office, we have what's called a flood forecasting centre, and we've got Environment Agency people and Met Office people working together. Now, it's a little bit like putting a jigsaw together, because the impact of rain can be different on certain occasions. If you take a certain amount of rain that is expected to fall, so that'll be the Met Office saying, right, we expect, say, 50 millimetres of rain to fall in that area tomorrow. So that's the first piece of the jigsaw. Now, if it's been very wet prior to that, then 50 millimetres of rain can cause huge impacts. I mean, we saw through the course of last year, as we had rain events on and on and on, that we needed less rain to cause major issues.
Because the ground's already saturated.
That's right, yeah.
Now, the predictions that we read from climate modellers is that if global warming, climate change and so on plays out the way that they are anticipating, we can expect to see more severe weather in future. In fact, some people are saying, look, hurricanes are already intensifying if you look at what's been happening in America in the last few years. So is the Met investing actively in more people doing your sorts of jobs and looking for patterns in order to meet this threat head on?
The simple answer is yes, because with the general temperature of the air across the globe heating up, it means it can hold a bit more moisture. I think we've certainly got to cater for the fact that the risk of extreme rainfall and the impact of that, of course, to be like flash flooding, as we've seen over the last few summers, we've certainly got to cater for that as happening more regularly than we've seen in the past. And that's the kind of information that is being fed to local authorities. We've got a set of scientists here working in a place called the Hadley Centre, and they're looking at possible scenarios in the future based on a warming trend. People that are then forecasting on a day-to-day basis, like myself and my team, we're also aware that those kind of challenges are going to be faced. And we may have to change our definitions of extreme based on what we're seeing. And we may need to think, or authorities may need to think about, how future drainage systems, town layouts, concrete, etc., may need to take into account some of the changes that we're expecting over the next, say, 50 years.
Thanks to Nick Graham from the Met Office.
The weather on Earth may sometimes seem pretty extreme to us, But across the solar system, even more wild weather phenomena are raging. The famous red spot on Jupiter, for example, is a hurricane. It's larger than the whole Earth, and it's been blowing for hundreds of years. To find out what we can learn from the weather systems on other planets, Dominic spoke to Professor John Zarnecki from the Open University. He started by asking where else in the solar system we might find weather that we would recognise here on Earth.
Well, of course, we're talking about places that have atmospheres, so we're generally talking about Mars, Venus, and actually my favourite place, which is Titan, the largest moon of Saturn, which also has an atmosphere. And we see some aspects which are quite familiar. We see clouds, we see winds, we see temperature variations between night and day, we see pressure systems. So in some respects, we see things that are familiar, but actually, if you look a bit more closely, then things start looking a bit different. I mean, for example, the temperatures are much more extreme, and then if you take Mars as an example, we have incredible dust storms, even sometimes dust storms covering the whole of Mars. So it's really a mixture of the familiar and the rather unfamiliar.
So is that just because these planets are at different distances from the Sun and receive different amounts of heating? Or does the chemistry of their atmospheres really affect the kind of places they are?
It's a combination of quite a few factors, really. Certainly the distance from the Sun has a big influence because, as we know, it's the radiation, the energy from the Sun that drives much of weather. So we've got Venus, which is closer to the Sun, and then Titan at the other extreme, which is about 10 times further from the Sun than us. So that's one factor, but there are other things. The pressure of the atmosphere, the amount of atmosphere, is very important. For example, Venus, very roughly, has a surface pressure about 100 times greater than us here on Earth. Mars, on the other hand, is about a factor of 100 times less than our surface pressure. The composition of the atmosphere comes into play, but perhaps less so than those other factors. And again, going back to the dust on Mars, that plays a big part because dust, you might think it's a bit inconsequential, but they're very efficient at absorbing sunlight, and then that is re-radiated into the atmosphere. So there's a factor of various differences which collectively make up these differences that we see.
Now, I guess the big surprise for me is that we're talking about Titan because we think of Venus and Mars as being quite Earth-like because they're relatively close to us in the solar system and they've been quite well studied. How does Titan manage to be similar to the Earth despite being 10 times more distant from the Sun?
Yes, it is fascinating, and Titan is basically an icy moon. It's mostly, at least the surface and the shell, is made of ice. And as you say, it's a lot further from us and a lot further from the Sun than we are. And yet, strangely, there are remarkable similarities and parallels. And that, I think, has surprised us. We weren't quite expecting that when we started studying Titan in great detail in the last 10 years or so. In particular, there is a material, liquid methane, which plays the same sort of role on Titan as water does here on Earth. It can exist as both a gas, a liquid, and a solid, and as a result, there is the equivalent of the water cycle on Titan. So methane sits in seas on the surface, it evaporates into the atmosphere, it forms clouds, and then it falls as rain onto the surface. So in that respect, we see systems on Titan that seem remarkably familiar. It's just that the materials are different, but the physical principles are essentially the same.
Now, obviously, we've got very detailed measurements of the weather that we have on Earth. We've got weather stations, we've got satellite images and radar. How does that compare with how much we know about the weather on other planets?
Well, that, of course, is an excellent point. We have, compared with Earth, quite sparse data. Having said that, Mars is now moderately well studied. We've had quite a few spacecraft visit it, which have taken observations over long time spans. And that is what you need, of course, to better understand weather. So we're beginning to build up a picture of the variability, particularly of Mars. And in fact, for Mars, there are in existence what we call global circulation models. So these are computer models which try to explain and predict how weather will vary across the whole planet. So in that respect, Mars is similar to Earth, in at least in our depth and range of our knowledge. For Venus, and especially Titan, the data is much more sparse, just, I suppose, because they're more difficult to observe. Venus, of course, is a terrible place to try and make measurements from the surface. It's horrifically hot, and the surface pressure, as I said, is about 100 times more than on Earth. So it's terribly difficult to put down a lander and have it survive for more than a few minutes. But we're gradually building up these models. And of course, why it's important, apart from intrinsic scientific interest, it does allow us to look at weather and physical processes which are occurring on the Earth, but we can observe them in a totally different environment. And that certainly helps us to make better models of weather here on our own Earth.
That's an interesting point, of course, because there are always people who will say, given the problem we've got on Earth, worries about climate change and so forth, is it worth investing in going to understand other planets when we could be worrying about our own planet? So what you're saying is that looking at weather elsewhere in the solar system can help us understand where the Earth came from and where it's going.
Absolutely so. Now, I wouldn't say that the entire business of space exploration is justified purely for that reason, but it is one of the bonuses that we get from it. And of course, the greenhouse effect, for example, which, as we know, is very important for us here on Earth, it's not something that is unique to the Earth. It occurs on other planets, certainly in an extreme case on Venus. We have an extreme greenhouse effect there, which is partly responsible for the very high surface temperature. And even on Titan, cold, distant Titan, there is also a small greenhouse effect in operation. So these are the sort of things that we study, we hopefully understand better, and who knows, in the long term, this might be quite significant in the way we better understand climate change and maybe respond to it also.
John Zarnecki from the Open University.
And if you've got any questions on weather forecasting or any of the other subjects we've been discussing on today's show, do let us know by emailing chris@thenakedscientist.com. You can tweet @NakedScientists, or you can find us on Facebook.
You're listening to The Naked Scientist with me, Chris Smith, and with Dominic Ford. And finally, Hannah's been breezing through this question of the week.
This week, we put a little pressure on to Wonder Wind. Pradeep Patel wrote in with this.
I want to know, what is wind and where does it come from? Not the type of wind you get from eating lots of baked beans, but the one that we feel in our face and see in the trees.
So what is wind and why is it with us? For the answer, we turn to meteorologist and weather forecaster Jim Bacon from WeatherQuest at the University of East Anglia.
The wind is what you feel when the molecules of air start moving. The question is, what makes them move? And this is the point where you can get a clue by listening to Queen's famous song, Under Pressure. Because it's a pressure difference that makes all of this happen. The atmosphere generally doesn't like things to be out of balance. It likes things all even. Just about any feature of the atmosphere would rather be in balance. Well, if you go to a place where there's a lot of air above you, the air is denser, the pressure at the surface is higher. And where there's less air above you, the pressure is lower. This is an imbalance, and it gives us areas of high and low pressure on the weather maps. And what the wind does is try to smooth things out by taking the air from where there's too much and moving it to where there's not so much. And the result of this is usually to reduce areas of high pressure and fill in areas of low pressure. Never quite achieves it, But the bigger the pressure difference that you start off with between high and low pressure, the quicker the wind wants to flow between them, and therefore you have a stronger wind. Well, it starts off, as you might reasonably think, blowing straight from high to low pressure. But because the Earth is spinning, other forces come into play, it gets a bit complicated, and in fact it almost ends up flowing around the highs and the lows, but slightly towards the lows, so it's always trying to fill in the lows. And you can see how fast the wind might be flowing by looking at a weather map, because on there you'll find lines of equal pressure, isobars, and when they're close together, this means there's a bigger pressure difference between the highs and the lows, and therefore the winds are stronger. In other words, the molecules that make up the air are under pressure to move from areas of high to low pressure.
Thanks, Jim. So it's the Earth's rotations and heat from sunlight that causes air density and pressure differences across the globe. And this results in wind. Well, sticking with the subject of natural phenomena, 13-year-old Chloe De Pinto wrote in with this.
I have planted beans and have watched them grow, and I would like to know what makes a plant grow upwards. I planted a bean in a pot and turned the pot upside down, but it still grew through the drain holes at the bottom of the pot. At the same time I planted a bean, waited till it germinated, then I turned the pot upside down. It then grew out, to the side and up. Why is that? Why does it always go up?
So do all plants grow upwards? And if so, why and how? Let us know your thoughts by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists, you can email studio@thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow.
And that is it for this week. Thank you to our guests, Brian Golding, Alison Ming, Nick Graham and John Zarnecki. Thank you also to Dominic Ford for joining me. The production this week was by Kate Lamble. Next week, we're going green-fingered because we'll be taking a look at the latest developments in the field of plant sciences. The Naked Scientists comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. My name's Chris Smith, and thank you for listening. Goodbye.